Welcome back to Montana.
Thank you so much. Thank you so much. What a pleasure to be here in this beautiful state, in this beautiful region around Bozeman. Tonight, I want to talk about evolution, a subject which, more than any other in science, causes stress and conflict, especially between science and religion. On the one hand, for some people, the first chapter of Genesis is enough. God created heavens and the earth. God created plants and animals. God created us in His own image. But scientists want something more. Scientists want to understand how God did it. And so we run into this conflict. And I ask you the question, should you believe in evolution? And in fact, do you believe in evolution? Okay, well I'm sorry, this is a trick question, because it's actually a very flawed question in two ways. It's flawed first because I haven't defined my term by evolution. People mean different things, and it's really important, first of all, to define that term evolution. And we'll see tonight that there are several different definitions, and the first thing you should do when you're having a conversation with someone is to figure out what that means. But more importantly, science is not about belief. It's not about believing in evolution. It's about assessing the evidence, looking at the natural world, seeing how it works, weighing alternative hypotheses, and then for the time, saying the hypothesis or the theory that fits most closely to the facts that we observe is this or that. And I think evolution fits that bill in terms of the biological process by which life has changed over time. But it's really not a matter that we as scientists believe in evolution. It's that the facts and the observations support this theory better than any other. So I want to do 6 things tonight. First of all, I want to just define evolution. I want to then look at some of the alternatives. If evolution isn't true, what are some of the other ways that things might change with time? I want to introduce the idea of emergent complexity, because for scientists studying this process, it turns out emergent complexity is a process which we see all around us, all throughout the universe, by which systems change, become more complex, more patterned, by which they evolve. I then want to is this going to stop working on me? There we go. Present examples of some complex evolving systems. This is kind of the meat of the talk, and we'll look at things like the origin of life and how minerals have changed through time. I think my battery is dead here. Review what Darwin said about evolution. And finally, and last but not least, I want to explain why I believe in evolution. That's kind of a joke. Okay, what's evolution? Evolution means a lot of different things. As a minimum definition, it means a change over time. And as we see, all different kinds of systems change through time, and life is no exception to this. But it usually means something more. For most of us, it means that there's a change, and this really isn't working anymore. Sorry about that. It means an increase in complexity and diversity and behavior, patterning. It means that somehow the system is becoming more interesting through time. And even more than that, it means that there's a series of stages, one after another, each one following from the previous one. So there's a logical continuum of steps. It's not just a random set of changes, but rather something where each step follows from the previous one. Now, in biological evolution, in Darwinian evolution, we also have this tenet of common descent. But we'll see that that's not a requirement in many evolving systems in the natural world. And finally, there's, of course, Darwinian evolution by natural selection. And when most people say, do you believe in evolution, what they're really asking is, do you believe in Darwin's version, Darwin's hypothesis, or Darwin's theory about evolution? So that's much more. If you just are talking about a change in time, it's obvious that this happens in all of our lives. It happens throughout the cosmos. But there's more and more restrictive definitions. Now, what's the alternative? The alternative. Now let's just look at one example of an evolving system, and that's something called chemical evolution. That's the origin of life, because it's something you can sort of focus on. There was a historic event, the origin of life. Now, it could have been a miracle. It could have been something, God created life. God created humans in his own image. And there's no way science can deal with that. You can't prove it, you can't disprove it. If that's the fact, then we just merely have to throw up our hands and acknowledge that somehow God is violating natural laws here and doing something that's outside the realm of physics and chemistry and the laws of nature that we can observe around us. Second possibility is that the origin of life is an event completely consistent with the laws of chemistry and physics, and yet extremely, exceedingly rare. Perhaps Earth's the only living planet amongst the 100 billion galaxies, each with 100 billion stars. And once again, if this is true, then science is at a loss to study the origin of life, because there's no way in a laboratory in a human lifetime you can study an incredible, improbable event. Even if it does conform with the laws of physics and chemistry, you're not going to be able to reproduce it in any systematic way. However, there's a third possibility, and that's that life is an inevitable consequence of the kinds of processes that take place on Earth-like planets, that life abounds in the universe, and in fact, this, for those of us who study origin of life, is kind of a philosophical underpinning. We can't prove it, it's not a scientific statement by any means, but we just have this hunch, we just have this feeling that the universe is pregnant with life and that planets like Earth are going to bring forth living worlds all around the cosmos. And there's a fourth possibility, and that's that life is the result of intelligent design, that there's an intelligence out there. Okay, so what do we do about this? For scientists, chemical evolution suggests that life arose by a natural process, what I'm going to call emergent complexity, and that the origin of life is simply a series of steps, chemical steps from simplicity to complexity, from geochemistry to biochemistry. Intelligent design, by contrast, talks about life being irreducibly complex. And so the argument goes, you're walking along, you look on the ground, you pick up a wristwatch, and you look at that, and even though you don't know who the designer was necessarily, you look at it and says, well, it's far too intricate to have just formed in a natural world. The materials, the juxtaposition, the gears, all these things, they work so perfectly. This had to have been designed, it had to be engineered, even if we don't know who the engineer was. And the same thing's true, because the simplest cell is, in many ways, far more complex than the most intricate engineered object on Earth. So here we have a hypothesis that in some respects conforms to natural law, but there's also a supernatural process here. There's the unseen designer, and of course the next step is who designed the designers. But that's the question. So how do you respond to this as a scientist? What do I say? Well, I say, okay, what I'm going to do is go into the laboratory and design a research program. I'm going to design a research program which experiment by experiment goes from geochemical simplicity to biochemical complexity. And if I can show that there's a series of steps that can be reproduced in any laboratory, that's plausible, that it mimics natural environments, if I can do that, if complexity arises spontaneously through emergence, then intelligent design is unnecessary. It's Occam's Razor. It's the idea that you don't need to add assumptions that stretch our credibility. You just stick with the things we know happen and we can demonstrate happen. Let me give you an analogy to this, and that has to do with Stonehenge, the great monument. 4,500 years old, it's on the southern plain of England, and there are books out there that claim that Stonehenge was built with the help of space aliens, the intelligent designers, that those stones are much too large for a human civilization with primitive tools to have lifted into place, and therefore flying saucers did it. However, you can imagine a scenario in which humans, using a lot of brute force, maybe 1,000 people, and also some ingenuity, dug holes, dug pits, had wood to roll the stones along, could chip them out with stone tools, put them into pits. They completed something like this, and you could make Stonehenge. Although it would take a lot of work. You could do it here on the Montana State University campus. You could get 1,000 undergrads, and over the next 10 years, you could make a Stonehenge trilithon, and it's perfectly conceivable. So why resort to space aliens? No one can disprove that space aliens helped make Stonehenge. No one can make that categorical statement, but in science, we accept a simpler explanation, and so it is with intelligent design. If I can show you that there's a process to go from simplicity to complexity, non-life to life through laboratory experiments, we don't need to resort to intelligent design. All right, part 3. So what is that process that would go from simplicity to complexity? It's something called emergent complexity, and we see it all around us all the time in so many examples. And the basic idea here is that systems become more complex over time when lots of individual particles or units, what are called agents in the field, interact with each other. So if you have sand grains, for example, each individual sand grain is exerted, but the force of gravity pulls it down. There's contact forces, the sand grains beside it, and then water or wind blows over it. And the result is an intricate variety of dunes and ripples and braided topographies and so forth. All the things we associate with collections of sand, but no one sand grain does that. And each individual sand grain is only responding to its local forces. So that's a very simple example. A much larger scale example is stars. Each one in a galaxy is responding only to local gravitational forces, and yet the collective behavior is these patternings, these spiral arms, the central bulge. And in life, we see this all kinds of interactions. Of course, neurons are the most amazing one, where each neuron of the billions of neurons in your brain is connected through dendrites to maybe 1,000 other neurons. So each neuron is responding again to relatively local stimuli, and yet the collective phenomenon is consciousness. No one neuron is conscious. So the emergent behavior is something that is outside the realm of the individual agent. It's a collective process. It's not magic, it's not mysticism, it's just physics and chemistry, but it's something that we see all around us all the time, and that's what the origin of life must have been, I think. So let me give you an example of one of my favorite emergent systems. This is the emergence of slime mold, what are called social amoeba. These individual organisms spend most of their lives as single cells on the forest floor, but given the right conditions, they send out chemical signals, they react to their neighbors, they start aggregating together. They literally form a slug-like creature that crawls across the forest floor. There it goes. And then it forms these beautiful stalk-like structures. A new generation of spores is released from the top, the next generation of dictyostelium, and then they melt away, and they go back to living as single cells. Extraordinary example where each cell is only responding to a local environment, and yet the collective emergent behavior is something vastly more complex. Now, this has been used in all sorts of contexts. I'm hoping I can show you a movie of this. One example is that you have to have rules of these interactions. Craig Reynolds, a Hollywood computer expert, designed a program called Boyds, in which he said, you can describe the flocking of birds, the schooling of fish, the swarming of insects with 3 vectors, shown in red here. And if you add these 3 vectors together, it tells you how each of these little boids should react. So each of these triangles is a boid. The vector, you try to avoid steering into your flock mates, but you also want to have something called alignment, that you want to go the same direction with your flock mates, and you also want to stay close to them. That's called cohesion. So you have 3 vectors, you can weight them different ways, and the result is something called these boids. But you have already seen this, so I don't really have to show you a movie, because everyone in this room has seen either Jurassic Park, herding of dinosaurs, you've seen Finding Nemo and the swarming of fish, you've seen the Batman movies with bats flying around, or the Mummy movies with swarms of insects. That's all done. That's why Craig Reynolds is now a millionaire many times over, because that little program of his has been used by all sorts of Hollywood people. Okay, well, so that's Boyds, and I had a wonderful YouTube video of flocking starlings. Go to YouTube, type in flocking starlings, look at this. If you haven't seen it, it's amazing. And it's just another example of swarming. Okay, and there are other examples which don't have to involve tangible physical agents. Here I'm talking about sand grains or birds or molecules or stars. But think about a note, an individual musical note, an abstract concept, really. And a single note by itself is nothing, it's just a note. But then you have rules, selection rules, and in every case there are rules of interaction. In music we call it harmony and counterpoint, and you put them together and you get music. That's an emergent phenomenon also. They're all around us all the time. There are thousands of examples. And that's what I think life is. I think life is an example of emergent phenomena. It happens at the molecular level, it happens at the cellular level, it happens at the level of social insects. Here are ants that are herding aphids. I mean, that's incredible. Each ant is only responding to local signals. It used to be thought there were only chemical signals and each ant responded to the local chemicals. Turns out it was just discovered recently that ants also emit very high frequency pitches. Which is just, I mean, that's wow. They communicate with each other. So it's chemical signals and apparently also these audio, very high-pitched signals. But there's still, it's only the local environment, yet they do all these amazing things. And in society, we see emergent phenomena too. We see agriculture, we see marathons, we see one of my favorite, the symphony orchestra. These are all collective phenomena. One individual can't do them. It has to be a collective effort. Okay. So what are some examples of complex evolving systems that display this kind of emergent behavior? I want to go through a series of them. I want to talk about elements and isotopes. I want to talk about mineral evolution. I want to talk about prebiotic chemicals and chemical evolution. So those are systems before life. Then languages evolve, material culture evolves, popular culture, and biological evolution. All of these display this kind of evolution. And one of the points to this lecture, which is in part a new rhetorical argument in favor of the idea of Darwinian evolution for biological systems, is if every system around us in nature shows this evolutionary pattern, why should biology be any different? Why should biology be the one system, the one complex system that doesn't show change over time through these selective mechanisms? Now, one of the things that's neat is all of these evolving systems have things that could be called species. They have selection criteria. They have diversification through time. They have niches that are filled. They have punctuation events where you have sudden increases in the diversity or complexity. And they also all have extinction events. These are common terms to all of these evolving systems. So let's take a look. Elements and isotopes. Okay, we start with the Big Bang. After the Big Bang, after a substantial period of time in terms of the early universe, you began to form, actually condensing out of this hot, expanding milieu. You actually condensed out hydrogen atoms, helium atoms, a little bit of lithium atoms. And so just from the Big Bang, you start then with a series of isotopes. And what this chart is showing you on the horizontal scale, mass number, that's how many protons and neutrons are in the nucleus. So you see hydrogen and helium all the way down to this end. And on the vertical scale is just a relative amount of those materials. So, right after the Big Bang, there are basically 4 isotopes, total 4 points on this graph. But those isotopes inevitably clumped together to form the first stars. And the first stars started synthesis processes, and those synthesis processes led to fusion reactions. Hydrogen synthesizes, it fuses to form helium, helium to form carbon, carbon you go through neon and oxygen and silicon and magnesium, all the way up to iron. This is the process of fusion that occurs in sun-like stars and larger stars. And so this is the second phase. And in the oldest stars in the cosmos, if we go back, we see that they've become richer in terms of their isotopes and their elements. But you see a lot of elements are missing here. What you need then is to have an exploding star. If the star gets large, if it gets all the way up to fusing to iron, but the iron no longer fuses, it no longer has nuclear reactions keeping the star expanding. So the star, with its nuclear fuel suddenly gone in the core, collapses down, and then it rebounds and explodes in a supernova. And in a supernova, because of the intense concentration, the pressure, energy, you have this fast neutron process, the rapid process, in which you start then adding neutrons on, building larger and larger and larger atoms until you basically make the entire periodic table of the elements. All of those heavy elements, all the gold and silver and lead and copper and zinc, these are all made in exploding stars. Every atom in a piece of gold jewelry like this ring was made in an exploding star billions of years ago. And so we see this gradual increase in complexity. And then as stars get older and older and they process this more and more, you go through the final stages and you have this incredible diversity. Roughly 2,000 known isotopes in the cosmos that are being produced continuously through the various stellar processes. So we started with 4 and we get up to 2,000. So this is an evolving process. We see extinction events, we see punctuation events with exploding stars, we see all the sort of characteristics of much more complex systems, and this is just elements and isotopes. Recently, I proposed a new way of thinking about mineralogy along these lines. This is called mineral evolution. And the idea here is you can look at the change in Earth's near surface through time. You can look at the diversity of mineral species. You can talk about the relative abundances of those minerals at the surface. The trace and minor elements that are present in those minerals change through time. Even the sizes and shapes, the crystal forms, change systematically through time for a variety of reasons. Let's just focus on this diversity of mineral species. It's amazing to me that mineralogists had not previously asked the question, what was the very first mineral in the cosmos? But after the Big Bang, you have to say, well, there was no minerals at the Big Bang, and there was no minerals in the first stars, so how could you form them? What you had to do is you have to form a star large enough that it formed carbon and silicon and oxygen and nitrogen in various layers, and then when it exploded, those layers expand, they cool, and when you got a place that's cool enough that the minerals can condense, but high enough concentration of elements, you get the first minerals. And I think the first mineral was diamond, followed shortly by graphite, and then carbides and some nitrides, a couple of oxides and silicates, about a dozen minerals in all. We call these the minerals, and they're still found today in the pre-solar grains, these dust grains that actually were the original building materials of our galaxy, of our planet, 4.5 billion years ago. And so the question is, how do you get from a dozen minerals, the minerals, to the more than 4,500 mineral species we see on Earth today? That's an evolution process. And it turns out that any planet or moon has three processes. One is the separation and concentration of chemical elements from their original, rather random distribution. The second is you get an increased range of temperature and pressure, partly because planets, as they grow, they have these internal variables. And on Earth, what turns out to be the most important process was life. Life itself forms minerals. You can think about three eras of the mineralogy of Earth. The first is when the meteorites were forming and planetesimals first came along. The second is when crust and mantle were reworked early in Earth history, right through to today, through things like plate tectonics. And finally, the era of biology and how biology changed mineralogy. And in our exposition, we talk about various stages of mineral evolution. The first has to do with the very initial heating, when the sun was triggered, when it became large enough to ignite. If you can imagine, you had the central sun, it held 99.9% of the mass of our solar system, and there's a disk around it of dust and gas. And when the sun ignited, there were pulses of heat that radiated out through that disk. It caused the dust to coalesce together, to melt into droplets and then cool. And you formed a series of meteorites called chondrites that hold about 60 different minerals. So you've gone from 12 to 60. And then those chondrites clump together. They form giant planetesimals, 200, 300, 400 kilometers in diameter, that internally melt, that differentiate, that undergo aqueous alteration and thermal alteration. They collide with each other, so they're shock minerals. And this gets you up to, and that's supposed to be 250, it's cut off there, 250 total known species in these achondrite meteorites. So we've gone from 12 to 60, now to 250. Now, we would argue then the next stage, you have planets formed like Earth and Mars and Mercury. The next stage would be to form full planets. And if you don't have a lot of volatiles, if you don't have a lot of water or other volatiles, you're pretty much stuck. And this, we think, is the end point of the Moon and Mercury. We think we're stuck at 350 mineral species. For some reason, this keeps getting cut off, and I apologize, but that's 350 mineral species here. We've gone from 12 to 60 to 250, now to 350. However, if you have a volatile-rich body, like Earth, like Mars, you can form a lot of other minerals, up to 500 species. And good heavens, this is getting stranger and stranger. But we think that 500 is as far as Mars can go. that Mars basically, because it's so small, it doesn't have a lot of internal heat to process. So even if there was water at or near Mars's surface, it didn't really form the giant ore bodies that we find on Earth. Now Venus may be different. Venus may have gone through a process of melting its basalt crust to form granite, which can produce maybe 500 more minerals. So I think Venus might be up around 1,000 different minerals. But Earth is different. Earth is a planet that has all of these rare minerals that form because of water-rock interactions. It takes 1 billion years to do this because you have to concentrate extremely rare elements like cesium and beryllium and lithium into smaller and smaller volumes so eventually they can crystallize out as these beautiful minerals that we find in our museums. But that's not going to happen on just any old planet or moon. You need to have a large volume, a lot of heat, and a lot of time. And then on Earth, we had another process. That's plate tectonics. Plate tectonics, because the plates subduct down into the center of the Earth, and they're very wet and rich compositions, they cause huge volumes of magma to rise and to reprocess and circulate through the crust. And you form massive sulfide deposits with hundreds of new minerals. You find all kinds of high-pressure terrains that are brought down into the Earth and pop back up. So new high-pressure minerals occur that never occurred before. And this gets up to 1,500 minerals. So see, we go from 12 to 60 to 250 to 350 to 500 to 1,000, now up to 1,500. And that's it. 1,500 is it. You cannot get beyond 1,500 minerals in an Earth-like planet. You can't unless you have biology. And what biology gives you is radically changed atmospheric conditions, particularly that toxic and extremely corrosive gas called oxygen. That creates a kind of surface environment where suddenly all sorts of new minerals become likely because of what's called oxidative weathering. So you have huge formations. The world's major iron ore deposits, the world's major manganese deposits precipitate out as oxides. And very quickly you have more than 4,000 minerals that are suddenly stable at or near the Earth's surface, just simply because of the presence of oxygen and the process of weathering. This is a consequence of biology. 2/3 of all the minerals on Earth are a consequence of biological evolution. Thousands of minerals would not have formed otherwise. If you go to Mars, if you go to Venus, you're not going to find turquoise. You're not going to find azurite. You're not going to find malachite. You're not going to find hundreds of minerals of uranium and nickel and iron and manganese and cobalt, molybdenum, on and on the list goes. And then 450 to 500 million years ago, Earth learned some new tricks called biomineralization, started forming minerals by life itself, where life learned how to precipitate calcium carbonate and silica, various other new minerals, and completely transformed the surface of the Earth. That's mineral evolution. And we see the coevolution here of the geo and the biosphere on our planet Earth. All right, so we've seen isotopes and elements, we've seen mineral evolution. Let's look at chemical evolution, or the origin of life. We think of life as evolving in 2 stages. The first is chemical evolution, the second natural selection, and I'll come back to that later when I talk about Darwin. But chemical evolution is the origin of life, and there are a few basic assumptions when we're thinking about this process. It's not exotic chemistry. We're all made of molecules, and so we're going to look at carbon chemistry. We don't want to talk about exotic materials. The origin of life was a process that relied on the raw materials available, the oceans, the atmosphere, rocks, and minerals. And we're going to think about the origin of life as a series of emergent steps of going from more simple to more and more complex. When I think about these emergent steps, I think about 4, each of which is amenable to experimental research in a laboratory. The first, biomolecules. You want to make amino acids, lipids, sugars, the building blocks of DNA and RNA. You then want to assemble those into the basic biological materials, polymers, cell membranes. You then need to have a self-replicating system of molecules, because that's the hallmark of life. And once you have a self-replicating system, then it begins to compete with slight variants of itself, and you get natural selection. And that's biological evolution, and that's that transition that we're talking about. So how does this happen? Well, the first step, that's the emergence of biomolecules. It's easy. You want to make carbon-carbon bonds. You start with simple volcanic gases with carbon shown in green here, carbon monoxide and carbon dioxide, for example. And then you form acetic acid with 2 carbons in a bond. You form pyruvic acid with 3 carbon atoms and so forth. Up and up you build it. Miller and Urey, the chemists at the University of Chicago in the 1950s, did this simple experiment where they simulated the oceans with a little bit of water that's been boiling. They had an atmosphere in there that represented what they thought was in the form of little electric sparks. And they made this incredible range of molecules just simply in a few days running this apparatus. They made amino acids, the building blocks of proteins. They made sugars, the building blocks of carbohydrates. They made lipids, which make cell membranes. They made fundamental molecules that are important to metabolism. They made building blocks of DNA and RNA, all in this simple glass apparatus. It looked like a balanced diet. People thought the origin of life problem had been solved. Of course, that was actually a setback in some ways because it took another 30 years for people to begin to experiment on other things like molecules forming in deep space, where you could simulate these dense molecular clouds in a vacuum chamber that was made very cold. You shone ultraviolet light on ice crystals. You make all those molecules. And our work at the laboratory in Carnegie Institution does the same thing, except we look at high pressure, high temperature environments of black smokers. And again, you subject simple molecules, volcanic gases, to these conditions, and you make all sorts of molecules. A simple reaction would have been pyruvic acid plus CO2 plus water. We put them in very modest conditions, 200 Celsius, 2,000 atmospheres, run this for 2 hours, the kinds of conditions you might find in a deep hydrothermal system. Now, in this particular experiment, I have to confess, we were rather naive. This was 15 years ago. The 3-carbon pyruvic acid molecule is one step in the citric acid cycle. What we wanted to show is if you add CO2, you get the 4-carbon oxaloacetic acid molecule. 3 plus 1 equals 4. If we show that in a simple paper, we'd have gotten famous. Tubes, we pressure, and they were all puffed up at the end of the experiment, a lot of internal pressure. So I carefully put them in liquid nitrogen to freeze the contents. I opened up by clipping off the end of the tube. Bang! You know, it just sort of like exploded. It was like there was a lot of internal pressure. I drop it into a vial, and as it thaws, it starts foaming and hissing. And this yellow-brown oily goo starts pouring out of the capsule. That's not oxaloacetic acid. That's something much, much more interesting. And then the aroma, it starts coming to you, and it permeates the laboratory. At lower temperature, it sort of smells like molasses. At higher temperature, 300 degrees Celsius, it's exactly like Jack Daniels. And people would come by the laboratory and they'd stick their head and they'd say, is there a party going on? Can I have some? And because it was really, and the thing is that there's an important point here. You're making really interesting organic molecules. You're not making oxaloacetic acid. You're making something that's much, much more complex and interesting. Things called aromatics and molecules that have that yellow-brown oily goo. And so this was amazing. We basically put this into a machine that analyzes the different molecules. And there's literally all these peaks of different molecules. There's hundreds, maybe thousands of different molecules here. Not just one, not just oxaloacetic acid. And this is actually an embarrassment of riches. We're making too much stuff. Life is very picky about which molecules it has, but this is just too much stuff. And so the second step in emergence is not one of making the molecules. That's really easy. It's selecting and concentrating just the right ones and organizing them into selection. So I was totally baffled what to do with this goo. And a good friend, Dave Deemer at the University of California, Santa Cruz, said, well, have you tried putting them in water? Maybe they'll self-organize. I said, huh? And he said, yeah, well, just try it. Just try. Just take a little drop of this stuff and put it in water, look at it under a microscope, and lo and behold, they self-organize. In other words, even though there's all that yellow-brown oily goo, some of them find each other and they make these little containers, these little things called vesicles. Just like a cell membrane has an inside and an outside. It's the same size and shape as many cells. This is not a cell, of course. This is just a chemical structure, but it's amazing to see how this works. And furthermore, we then did experiments saying, well, how else might we select and concentrate from this vast organic soup just the right molecules? And it turns out that many molecules will automatically, spontaneously come out of solution and stick to mineral surfaces. They'll align along a crystal structure. They'll template themselves. And so here we have a mechanism. We've made the molecules. Now we can select, concentrate, and organize the molecules. So those two steps, I think, are pretty well understood, at least generally, if not in quite some detail in some cases. The problem is, of course, making a self-replicating system, and that's the thing that's still very much at the frontier of research and origin of life. So don't think that we're done. The fun thing about getting up in the morning and going to the laboratory is the things we don't know. So finding that self-replicating system is going to occupy people for some time. But I wouldn't be surprised if the next 10 years or so that becomes routine and that we can have a system where we start with the molecules, they organize, they self-replicate, and that's basically the origin of life. Lots of other complex evolving systems out there. And languages are surely one of them. You've seen these branching trees of language because there is a kind of common descent to language. But language has other properties. They're extinction events. Languages go away if people stop speaking them. And I was amazed to think about the punctuation events. This is an article that appeared in Nature a few years ago, which said that the publication of Noah Webster's new American dictionary, I believe it was 1812, was a punctuation event. If you look at American newspapers the year before and the year after, you'll find that before they conformed very much to British newspapers in the use of the English language. But the year after, American and British newspapers used a very different vocabulary and spellings. It was a break, it was a punctuation event in the dispersal of English. So languages have these kinds of properties. And then, of course, material culture shows incredible evolution. And you can imagine thinking about bicycles or automobiles or computers or cell phones or whatever you want. One of my favorite examples is in the musical world in the trumpets. In the 18th century, trumpets were just long, straight tubes. They just played like a bugle. You just used your lip and you could play only the harmonic overtones. Well, trumpeters got pretty bored of doing that, and in the early 19th century they invented something new called the keyed bugle. It lasted for about half a century. These keys, the flapper keys on the side of the bugle, allowed you to play a chromatic scale, but it had a rather uneven sound and was very awkward, and especially in marching bands they tend to break a lot. You know, if you break a key and you're outside, there's not much you can do about it. So it kind of went by the wayside and was replaced then, especially after steam engine technologies came in and you could make airtight valves, what's now the valved trumpet, which can play all the things that the trumpets play that you've heard. And so this is an evolution, and it's the same kind of thing. And you see punctuation events, you see invention. You also see something called lateral transfer in material culture, something that biologists talk a lot about with microbes, where different genetic components can actually be transferred wholesale from one microbe to a lateral transfer. It's a different kind of evolutionary process. And then there's popular culture, and if my videos were playing, I would play you clips of some very early Broadway musicals which look rather primitive and crude to us, which no one would pay for now, because of course there is a selection process in Broadway musicals. People have to like it, they have to pay money to go to it, that's selection. And so you have these early Broadways, and you have the sort of classics, Carousel in Oklahoma, which really had a kind of classic dance number. They actually had ballet being used as the principal dance source. And then in the 1950s, you got much more into jazz sort of dance and jazz music being incorporated into the Broadway musicals, as in Kiss Me, Kate. And then that great transformative musical, I wish I could have played it for you, from West Side Story, where you see the merging of classical and jazz influences and a totally new kind of musical rhetoric used, and that really changed the theater forever. And that's one of the things about evolution. Each time you go from one step to another, you can't go back. I mean, it's like you've reached a new stage, and that's the thing that's so exciting about living in the modern age of material and popular culture, because we keep seeing year by year this evolution of what's going on. Okay, so now we're talking about biological evolution. What did Darwin say, and how does it fit in with what I've just presented? Well, first of all, I suggested the origin of life is the arising of the first self-replicating system. Think of that as the first cell. And that first cell had no competition, so it kept dividing and evolving, filling the ocean bases. It multiplied rapidly. It also evolved because there's And there were lots of different niches. There were salty or in fresh water. There was high pressure and low temperature, low temperature, day versus night, you know, rocky versus different kinds of mineral surfaces and so forth. And so you had basically this radiation and this selection into niches and punctuation and diversification. That's what Darwin was talking about. And it's amazing that he came to this idea that we are all descended somehow from that first common cell through common descent. And his evidence, his principal evidence, observational, had to do with the beaks of finches, where he went to the Galapagos Island and saw that on different islands, different birds that had different diets, whether they were cracking nuts or trying to get insects with long beaks or eating berries and so forth, evolved in different ways. And I think it's an incredible stretch for Darwin to have come up with his theory just based on this kind of evidence, the small variations, what many people call microevolution, changing. But Darwin still had this vision that somehow you could go through major changes. He recognized that this was challenging. He talked about eye evolution. And in the first part of this quote, which is often reproduced in creationist literature, Darwin is expressing his own doubts. You know, it's as absurd in the highest possible degree to think that you could go from a non-eye to an eye, except, he writes, reason tells me that if numerous gradations from a simple and imperfect eye to one complex and perfect can be shown to exist, each grade being useful to its possessor, as is certain the case, if further the eye varies and the variations be inherited, as is likewise certain the case, then the difficulty of believing that a perfect and complex eye could be formed by natural selection should not be considered as subversive of the theory. That's what Darwin said. And in order to sort of demonstrate and test this idea, almost 20 years ago now, two scientists created a computer program of an eye from not an eye. And if you have, amazing, and it shows you something about the power of selection and variation. Here's the idea. Any increase in visual acuity provides an advantage to, for example, a worm dwelling on the bottom of the ocean. There are predators that swim by. If you can see a shadow, you may be able to escape. And if you can see the direction from which the shadow is coming from, all the better. And if you can tell how far away the object is that's making the shadow, all the better. And so you start out with the back of a worm here. In black is just a bunch of cells or whatever is below supporting. In gray are a series of light-sensitive cells. And this is not a stretch. We know that there are light-sensitive cells all over, that your skin gets sunburned, that's a light-sensitive cell. And in fact, there are many microbes, individual cells, that when you shine a light on them, they actually move away to a darker part of a petri dish. In other words, they're light-sensitive in some way. And then at the top part, the clear layer, is a layer of protective cells that's transparent. And what Nelson and Pelger said is, let's use a computer and vary 3 parameters randomly by plus or minus 1%. Let's vary the radius of curvature. It can either curve outward or it can curve inward by plus or minus 1%. Let's vary the aperture. That's the distance between the two endpoints here. We can vary that by plus or minus 1%. And let's also change the amount to which that clear layer bends light. That's something called refractive index. It's what your glasses do when they bend light. And let's change that by plus or minus 1%. And if a change increases visual acuity, you preserve it to the next generation. And if a change doesn't increase visual acuity, you just ignore it. And so what happens? You vary these things, you improve them. After just a couple of hundred steps, you get a little indentation, slight curvature. All this means is you can tell that there's a shadow and what direction it's coming from. You go to a few hundred more steps, and you get something that looks like an eye pit. And indeed, after about 1,000 steps, you have a spherical eye pit. And there actually are organisms. The lymph, for example, I believe, has an eye that's very much like this. There's no lens. There's just light-sensitive cells here. That's after 1,000 steps. And by the way, this happens every time you run this computer simulation. Even though they're random steps, the selection is not random. But wait, there's more. Then you start forming a lens because the index of refraction starts to change spontaneously. And you get more of a lens. And after about 1,800 steps in this simulation, you have a perfect, mathematically perfect eye based on this starting configuration. It's a perfect lens, it's a perfect focal length, so this is as good as an eye can possibly be. If you were to engineer this, you couldn't do better. And every single time you run the simulation, you end up at the same point. In other words, it's random variation with a very simple selection rule, and yet the result is deterministic. Eyes are deterministic. They have evolved, according to the fossil record, at least 40 and maybe 60 separate times in Earth history. And it evolves by this process. There is a random element, and that's just the plus or minus variations, the mutations. But selection is not random. And this is the fastest, easiest, most efficient way to produce an eye. That's why we say, if evolution is real, then the way God did it is certainly like this and not by intelligent design. So, part 6. Why do I believe in evolution? Well, the first reason I think I can see these complex systems all the time. This is unique to biology. In fact, quite the contrary. Elements and isotopes, minerals evolve, chemicals evolve in the prebiotic environment, languages, material culture, popular culture all evolve. Why should biology be any different? Second reason why I believe in evolution is it makes testable predictions. Contrary to what some people would say, Darwin makes millions of specific, very detailed predictions, particularly about where to go for fossils. 25 years ago, the creationists took this tack. They said, it's an embarrassment to Darwin that no one has ever shown an intermediate form between a land animal and a whale. And the lack of these fossils is essentially proof that Darwin was wrong. And you know what paleontologists did? They went, the vertebrate paleontologists said, yeah, that's exactly right. We haven't really gone out and looked in formations of the right age. We know that 60 million years ago there were land mammals, today they're whales. That means if you go to places that are 20 or 30 or 40 or 50 million years old, in shallow marine environments like Maui today where whales would have come to calf, we should be able to find whale skeletons, and they should show, as you go farther back, longer and longer vestigial hind legs. That's a prediction. We completely agree. And so they did that. They went to Egypt, they went to Pakistan, they went to Chile, they went to Alabama. They looked at the right, and they found 50 million years ago, they found the Ambulosotetus, a walking whale, a rather awkward-looking creature. But let's face it, I mean, seals today are rather awkward-looking creatures. This isn't that far-fetched. But it has whale-like and land animal-like characteristics. And they looked at 46 million-year-old. Here's the beautiful Rhodocetus. Look at those hind legs getting smaller, and the front legs getting more and more flipper-like. And then there are others. There's the Basilosaurus, and there's the Georgocetus, and all sorts of others. Here's a Basilosaurus skeleton found not terribly long ago, and it has a little vestigial hind leg. The hind leg is only about 1.5 feet long. If you go to the Smithsonian Institution, you can see this specimen. And it's really quite remarkable. That's a vestigial hind leg. And just as predicted, this is about 35 million years ago, and the legs get shorter and shorter and shorter through time. That's a prediction. Darwin makes these predictions. So the power of evolution is that it makes these predictions. You can go out and test the predictions. And in every single case that we've tried so far, that in the right formations of the right age, you find fossils that are intermediate between the ones that are younger and the ones that are older. That's the power of evolution. And finally, on a more philosophical note, the reason I believe in evolution is that the alternative, this idea of God in the gaps, is philosophically unacceptable to me. God in the gaps, the idea that, gee, there's a land animal 50 million years ago, here's a whale today, and there's nothing in between, so God must have done it. Okay? Because that's a big gap. But then you find Ambulosotetus, and you find Rhodocetus, you find Basilosaurus, and you find Georgocetus. And God is starting to look very small to me. Do we really need God to make every one of those intermediate creatures? My wife, Margie, and I, we collect trilobites. We've been collecting trilobites for more than 40 years. And trilobites are amazing. Here are some of the specimens from our collection. Just 15, we have over 2,000. And you see the variety of these trilobites. Now, These look all pretty different from each other. I mean, they're all recognizably trilobites. But when you start adding the thousands of others, there's some 20,000 known species of trilobites, filling in the gaps. And you can see a complete sequence from the most primitive trilobites 530 million years ago to the ones, and the very last ones who died out about 250 million years ago. Now, certainly an omnipotent God could create every one of those 20,000 species. But what if there's a process by which it happens spontaneously through natural law? And so I want you to think about it this way. Look, I know that for many people this idea of evolution is troubling. How can we be created in God's image if we're the product of some random mutations and some selection? It might have happened, it might not. But think of it a different way. We live in a universe that began in a Big Bang, which produced hydrogen and helium. And the hydrogen and the helium inevitably came together to form giant stars. And the giant stars, through fusion, produced all the other chemical elements, and they exploded, seeding the universe with the entire periodic table of the elements. And then the periodic table comes together to form planets, Earth-like planets. And on Earth-like planets, you have an evolutionary process too. First of minerals, and then possibly of life. And from life, perhaps intelligence also, and humans and other species are an inevitable process. And so we see through this progression, this inevitable progression of emergent complexity, a universe that is learning to know itself. Thank you very much.